this video, we're going to prove the following theorem. It's called the Mobius Inversion Formula. It goes on to say, let capital F and little f be two number theoretic functions related by this formula. And we want to show that this summation is equal to f of n. So how about we get right into this, except we have a little commercial break. If you guys like watching proofs of theorems and lemmas and corollaries, you should consider subscribing to my channel, as that's all we do here. Okay, back to the proof. This, which is the summation of mu of d times f of n over d, as we sum over all divisors of n. Well, this is equal to the summation as we sum over all divisors of n of mu of d times this. Well, basically, n is being replaced, as you see, with n over d. So we have the summation, and instead of d, I'm going to use c, because I already used d in the first summation, as c divides n over d of f for c. In the first one, it was the summation of what I put around the brackets. Same thing here. Now, this is the same as the summation as d divides n of the summation of c divides n over d of mu of d times f for c. That is, I can put this in here because this is just summing over c, and that's not a function of c. When it comes to c, it's a constant. So I can put it in there. Okay. Now we have this fact. You can prove it. It's not that hard. D divides n and c divides n over d if and only if c divides n and d divides n over c. So this and this guarantees that. So this we can write as the following. We can write this as the summation as c divides n of the summation of c divides n over d. Actually, d divides n over c. I'll write this first. F for c times mu of d. Okay. Now, I can play games with the brackets. This is the summation as c divides n times the summation d divides n over c of f for c times mu of d. In fact, this first summation is only involving d. I can bring that in front. So this is the summation as c divides n of f for c times the summation as d divides n over c of mu of d. Now, note, now we proved this in our prior theorem. Note that the summation as d divides n over c of mu of d is equal to 0, except except when d divides 1, when n over c equals 1. But if n over c equals 1, that implies m equals c. So the only time this is not 0 is when n is equal to c. Okay, so how about we say that? It's the summation as c equals n, or n equals c, of one last comment. This is equal to 0 except when n over c equals 1, and in that case, the summation as d divides n over c of mu of d is equal to 1. That's important. Okay, so coming down here, we have the summation as n is equal to c. Well, let me say it the other way. C equals n of that times that. But that's 1. Well, this is the summation as c equals n. This product is just f for c, and c is n. There's only one value for c. I'm going to sum over all of these values of f for c. But there's only one value. And that value of c is n. That's what I wanted to show. I wanted to show that this right here is equal to f of n. That's exactly what I said, what the theorem told me to show. That's what I showed. Proof is done. If you like seeing math proofs like this, you should seriously consider subscribing to my channel, as that's what we do in this channel. We prove mathematical facts. Subscribe to my channel, click the like button, leave a comment, come view my next video, watch and learn.